Have you ever wondered why gold nanoparticles shine red instead of gold? Or why quantum dots can glow in every color of the rainbow? The reason is something called quantum confinement, one of the most fascinating effects in nanoscience. When materials are made extremely small, down to a few nanometers, the electrons inside them lose their freedom to move. Imagine electrons as musicians in a concert hall. In a large hall, representing a bulk material, they can play almost any note. But when confined to a tiny room, a nanoparticle, only certain notes or energy levels fit. This restriction causes energy levels to separate. What actually happens when the particle gets smaller? As the size of the material gets smaller, its allowed energy states become discrete rather than continuous. The smaller the particle, the larger the gap between these states. This means it takes more energy to excite an electron, or in simple terms, the material's band gap increases. A cadmium selenide quantum dot can emit different colors just by changing its size. A large quantum dot might emit red light, while a smaller one glows blue, even though both are made of the same material. By tuning the size, scientists can literally choose the color. One material, infinite colors, all controlled by quantum mechanics. Let's understand the physics of quantum confinement mathematically. The energy of a confined electron is inversely proportional to the square of the confinement length L. As the confinement dimension L decreases, the separation between energy levels increases dramatically. When the particle is very small, the energy levels are widely spaced, requiring more energy to excite electrons. Quantum confinement is more than just a pretty light show. It's the foundation for many modern technologies. Quantum dots are now used in high-definition displays, providing vivid colors and better contrast. Medical imaging uses quantum dots as bright, stable markers that can track biological processes in real time. Solar cells use quantum confinement effects to tune light absorption and improve energy conversion efficiency. The same principle applies in nanowires and thin films that control how electrons move in transistors and sensors. When you shrink matter to the nanoscale, you're not just making it smaller, you're changing its very nature. As we move from bulk to micro to nano, the quantum effects become increasingly dominant. Energy levels transition from continuous in bulk materials to discrete in nanoparticles. In this tiny world, size is not just a physical dimension, it's a control knob for the quantum behavior of light and matter. Let's summarize what makes quantum confinement so remarkable. Quantum confinement occurs when materials shrink to the nanoscale, where quantum effects dominate. Smaller particles have larger band gaps, causing them to absorb and emit light at different wavelengths. The same material can produce a rainbow of colors simply by controlling the particle size. Applications span from brilliant displays to medical imaging to more efficient solar energy harvesting. Quantum confinement reveals the beautiful connection between size, quantum mechanics, and the properties of matter at the nanoscale. Explore how tiny particles trapped in boxes reveal the quantum nature of matter. When we trap an electron in a tiny box, quantum mechanics dictates that its energy becomes quantized, like a guitar string that can only vibrate at certain frequencies. Let's understand how the size of confinement affects the electron's energy. The ground state energy of a confined electron is approximately h squared over 8 meters L squared, where L is the box size. As the box size L decreases, the energy E increases dramatically, following an inverse square relationship. Here's a graph showing how ground state energy varies with box size. At 10 nanometers, we get 3.8 millielectron volts, but at 2 nanometers, it jumps to 94 millielectron volts. Now let's compare these quantum energies with thermal energy at room temperature. At room temperature, 300 Kelvin, thermal energy kBT is approximately 26 millielectron volts. This bar chart compares quantum energies at different sizes with the thermal energy line. Below 3 to 5 nanometers, quantum level spacings exceed thermal energy. When L is less than 3 to 5 nanometers, the discrete quantum levels dominate over thermal fluctuations. Let's examine a concrete example comparing quantum dots of different sizes. A 3 nanometer quantum dot has energy 42 millielectron volts, much larger than the 3.8 millielectron volts of a 10 nanometer dot. In the 3 nanometer dot, the energy gap exceeds thermal energy, so electrons remain in the ground state, producing sharp optical lines. In the 10 nanometer dot, the gap is comparable to thermal energy, so thermal smearing washes out the discrete level structure. The excitant Bohr radius tells us when quantum confinement effects become important. The effective Bohr radius equals the dielectric constant times the ratio of free electron mass to effective mass times the hydrogen Bohr radius. Strong quantum confinement occurs when the particle size is less than this effective Bohr radius. For gallium arsenide, the effective Bohr radius is about 10 nanometers, while for cadmium selenide, it's about 3.9 nanometers. Quantum confinement produces dramatic color changes in semiconductor nanocrystals. A 3 nanometer cadmium selenide core emits blue light, while a 6 nanometer core emits red light, demonstrating size-dependent emission. At 3 nanometers, below the Bohr radius, electron-hole motion is squeezed, raising kinetic energy and widening the effective band gap. At 6 nanometers, above the Bohr radius, carriers behave more bulk-like, so the energy shift is much smaller. The Briss equation gives us a quantitative formula for the confinement energy shift. The energy shift has two terms: a positive kinetic confinement term scaling as 1 over r squared, minus a negative Coulomb term scaling as 1 over r. The first term represents the kinetic energy increase due to spatial confinement of the electron and hole. The second term represents the enhanced Coulomb attraction between electron and hole in a smaller volume. Let's calculate specific numbers for cadmium selenide quantum dots at different sizes. For a 3 nanometer radius dot, the energy shift is 0.41 electron volts. Shrinking to 2 nanometers nearly doubles it to 0.80 electron volts. This dramatic change occurs because the confinement term scales as 1 over r squared. Shrinking the core from 3 to 2 nanometers shifts the emission by about 0.4 electron volts toward the blue, roughly 100 nanometers shorter wavelength. Let's visualize why such small size changes have such large effects. In a large box, the electron wave function has a long wavelength and low kinetic energy, like a loose guitar string. In a small box, the wave function is squeezed to a short wavelength and high kinetic energy, like a tight guitar string. Let's summarize the key insights about quantum confinement. The quantum confinement energy scales as 1 over L squared, making small changes in size produce large energy shifts. Below 3 to 5 nanometers, quantum energy level spacings exceed room temperature thermal energy, so discrete levels dominate. Strong quantum confinement effects appear when the nanostructure size drops below the material's effective excitant Bohr radius. These principles enable technologies like size-tunable quantum dot lasers, bright LED displays, and single photon sources for quantum communication. Let's explore how quantum particles can tunnel through barriers that would be impossible to cross in classical physics. In quantum mechanics, particles can tunnel through energy barriers, appearing on the other side even though they lack the classical energy to go over. First, let's understand what quantum tunneling is and why it matters. Quantum tunneling is a phenomenon where particles penetrate through potential barriers that would be impossible to cross classically. The transmission probability T is approximately exponential in the barrier thickness A, with decay constant kappa. Kappa depends on the effective mass m star, the barrier height minus particle energy V minus E, and Planck's constant. Here's a potential energy diagram showing a rectangular barrier of height V and width A, with a particle of energy E approaching from the left. Let's calculate tunneling for a standard semiconductor barrier. For our first example, we use an effective mass equal to the free electron mass and a barrier height of 1 electron volt. The barrier width is 2 nanometers. Calculating kappa using the electron mass and energy values gives us the decay constant. This gives kappa approximately 5.1 times 10 to the 9th per meter. The transmission probability is about 3.6 times 10 to the negative 9, which is extremely small. With a high barrier, almost all the incident wave is reflected, with only a tiny transmitted component. Now let's see what happens when we reduce both the barrier height and effective mass. Using an effective mass of 0.19 times the electron mass and a barrier height of 0.3 electron volts. This gives us a much smaller kappa of about 1.25 times 10 to the 9th per meter. The transmission probability jumps to 7.5 times 10 to the negative 3, which is about 0.75%. By reducing the barrier height and effective mass, we increase the transmission probability by a factor of about 2 million. With a lower barrier and smaller effective mass, a significant portion of the wave now transmits through. Let's apply this to quantum dots separated by a thin barrier. Consider two quantum dots, each 3 nanometers in size, separated by a 2 nanometer barrier. The wave functions in each dot can overlap through the barrier if tunneling is strong enough. With a high bandgap oxide barrier, the dots remain electronically isolated with no coupling. Replacing with a lower barrier material allows wave functions to overlap, creating coupled states. In the isolated regime, transmission is around 10 to the negative 9. In the coupled regime, transmission increases to around 10 to the negative 3. Now let's understand the charging energy of tiny quantum dots. When you try to add an electron to a tiny quantum dot, it costs energy because of the dot's small capacitance. The capacitance scales with the dot radius r and the dielectric constant epsilon r. The charging energy equals E squared over 2c. For a dot radius of 5 nanometers in a medium with dielectric constant 10. The charging energy is about 14 millielectron volts. Shrinking the radius to 2 nanometers, the charging energy increases to 36 millielectron volts. With pore screening and epsilon r equals 2, the charging energy jumps to 180 millielectron volts. This creates a staircase pattern in the current voltage curve, where current only flows when the bias supplies enough energy to add another electron. We can estimate confinement energies using Heisenberg's uncertainty principle. The momentum uncertainty is roughly h over 2L, where L is the confinement length. The energy is approximately delta P squared over 2 meters. Combining these gives energy proportional to 1 over L squared. For a confinement length of 5 nanometers, the energy is about 15 millielectron volts. Shrinking to 2 nanometers, the energy increases to about 94 millielectron volts. Having the confinement size roughly quadruples the energy, explaining why smaller quantum dots emit bluer light. Let's summarize the key quantum confinement effects. Quantum tunneling probability drops exponentially with barrier thickness and height. Even small changes in effective mass or barrier height can change transmission by orders of magnitude. The charging energy scales inversely with radius, so smaller dots have much larger charging energies. Confinement energy increases rapidly as size decreases, following a 1 over L squared scaling. Let's explore how to engineer quantum dots and quantum wells for specific optical and electronic properties. Quantum confinement allows us to tune the optical properties of semiconductor nanostructures by controlling their size. Our first design problem is finding the right quantum dot size for a specific energy shift. We want to shift the emission of cadmium selenide from red light at 650 nanometers to green light at 550 nanometers. This wavelength shift corresponds to an energy increase of about 0.4 electron volts due to quantum confinement. Using the Bruss equation, we find that a radius of approximately 2.7 nanometers produces the desired 0.4 electron volt blue shift. Therefore, our target radius is 2.7 nanometers. Now let's see how to implement this design in practice. We synthesize cadmium selenide cores with 2.7 nanometer radius, then coat them with a zinc sulfide shell to passivate surface states and lock in the green emission. The shell not only protects the core, but also fine-tunes the confinement through dielectric effects and strain. This transforms bulk red emission at 650 nanometers into bright green emission at 550 nanometers. When we confine structures to nanoscale, even lattice vibrations become quantized. The lowest acoustic phonon frequency scales inversely with the box size L, where V is the sound velocity around 3,000 meters per second. For a 5 nanometer box, the phonon frequency is about 3 times 10 to the 11 Hz, giving an energy of 1.24 millielectron volts. For a smaller 2 nanometer box, the frequency increases to 7.5 times 10 to the 11 Hz, and the phonon energy rises to 3.1 millielectron volts. In low-temperature spectra, we observe phonon sidebands separated by these few millielectron volt spacings. Quantum wells allow us to engineer sub-band transitions for specific applications like terahertz detection. We want to design a quantum well with the first sub-band spacing of 50 millielectron volts. The sub-band energy scales as h squared over 8 times effective mass times well thickness squared. For gallium arsenide with its light effective mass, an effective mass of 0.067 times the electron mass requires a well thickness of about 10.6 nanometers. For silicon, with its heavier effective mass, an effective mass of 0.19 requires only 6.3 nanometers to achieve the same 50 millielectron volt spacing. The well thickness L directly controls the sub-band spacing, with heavier effective mass materials requiring thinner wells. Let's summarize the key design principles for nanostructure engineering. For quantum dots, the radius controls the energy gap through quantum confinement effects. The energy shift scales inversely with radius squared. In smaller nanostructures, phonon mode spacings increase, affecting optical line widths and relaxation dynamics. For quantum wells targeting a specific sub-band spacing, materials with lighter effective mass require thicker wells. The required thickness scales inversely with the square root of effective mass times target energy. By understanding these scaling laws, we can precisely engineer quantum dots, quantum wells, and phonon modes for specific applications.